it comes to the front, right? So because there's no loudspeaker. I have to yell, but my voice is not very strong. Ready? All right, let's get started. All right, this is my last. So we're going to talk about population coding and decoding. So we all know that the information in the brain is distributed among many neurons. So each individual neuron may not carry as much information as necessary to do some task. So one classic example is this cosine tuning curve in the motor cortex. I'm sure you already heard of this example. So here on the left is a monkey moving his hand in different directions, starting from the center and reaching out to 8 different directions. So this is raster plot the firing rate of a single motor neuron in the motor cortex. All right, a single neuron in the motor cortex. So you can see the cell fires a lot when the animal moves in this direction, and fire less when you move in the other direction. If you plot the firing rate of the neuron as a function of the movement direction of the hand, you get a curve look like this. So basically it's a cosine function. Right? Of course the preferred direction may be different, depend on the cell. So the question when people first discovered this is that when you ask a monkey to move his hand, the hand movement is much more accurate than this very broad curve. You see that this tuning is very broad, right? If the cell have high firing rate, this many degrees, right, tens of degrees, it's very wide. So the question is, if individual cell carry information in such an imprecise manner, how is it possible the hand movement can be very precise? So hand movement is much more precise than tens of degrees. That can just less than 1 degree can be extremely precise if you're trained to do something. So to make a very precise movement, then you have to use information from many neurons. Right? Because the motor cortex is supposed to be the the output stage of the brain that make command to make fine movement. So if each of a neuron work like this, you don't see neurons very sharp tuning. They are all very broad like this. Right? So how is it possible you have a very precise movement? So that means this is inevitable. You must use information from many neurons at the same time. Right? So this is a very common thing in many systems. Like this auditory system, this doesn't show the firing rate, but it shows the threshold of a neuron. It's basically auditory nerve. Right? It's you'll notice that each nerve fiber, auditory nerve fiber, they like a particular frequency. So if you play that frequency, the threshold to drive the nerve is lower. So that means this cell like this frequency. So there are many neurons that like all different frequencies. Right? There's some overlap. And you see that. So if I play a sound at some particular frequency, you activate all the cells with the preferred frequency that's very similar to your actual frequency. But the cells that are very far away, they don't care. Okay? Your information is really, if you play like music, you play harmonics, and multiple tones play at the same time, you activate multiple cells at the same time. Right? It's not just single cell. Whatever you perceive you must base on information carried by many neurons. So there's another example in the somatosensory system. So these is a monkey's hand, very long, look like alien. So the circle, the ovals here means the receptive fields of a neuron in the somatosensory cortex. So basically you touch the skin, only when you touch inside the receptive field, you're able to drive that neuron. If you touch outside, the neuron doesn't care, right? That's just receptive field, similar to the vision. You can see a few things. For example, maybe in the fingertips, maybe the cell is slightly smaller, maybe these are bigger. But the point is, you look at the size of the receptive field, it's pretty big, right? And people can, a monkey, you can sense whether there are 2 needles, pointing on your head versus 1. There are some thresholds. The threshold is much smaller than the size of the receptive field. Right? To make that distinction, you have to use information from more than 1 neuron. If I just only 1 neuron, suppose my needle falling, into this receptive field of a single neuron, that cell has no idea what's inside, just activated. If you want to tell whether there's 1 versus 2, you have to use information from multiple neurons. So this is a very general thing. The visual system, of course, you know the color vision. Color vision, of course, the thing that we can see many different colors, but the inherent dimension is only 3 dimensions. That's proven by this projector, right? The projector projects only 3 colors, as you know. And for any color, like a brown, like a pink, whatever color. So these are, you must activate more than one cell. Typically you activate all 3 different color cones, different ratios. Right? So all the perceptible complex colors, all the fancy colors, they're not just single cones. It must be activation multiple cones, and their combination give you that perception. Right? One more example. This is a visual reception field of I think the ground squirrel. So what is shown here is that each of the oval here is a reception field of a single neuron. So there are many of them. You see the fovea is here. You're looking at here. So usually if you shine a light inside this small oval, the cell is activated in the cortex or visual cortex of this squirrel. And the size of the reception field is bigger if you're further away from the fovea. Like it says here is over representation of this, and you're very precise here, but not very precise here. But even that, your visual acuity is much higher than the size. You can actually, for human, we don't know about squirrel, but presumably similar. But if you, like say, I want to ask you to tell whether 2 lines, they're aligned versus slightly offset. People are very good at this. You can tell if even there are small misalignment, you can actually see they're not exactly aligned. And turns out that small disalignment, small difference is actually smaller than the size of the cones. The color cones, all this in your retina. Right. That means you really the 2 different lines. That difference actually fall into the size of a single cell. So to actually do the task like a hyperacuity, you can see the difference. You must use pull the information from many cells. Right? So I think that all these examples give you a single, it's a single theme. Right? Really, you need many cells used at the same time to do something. Actually, brain use that. Right? Just by information point of view, this is inevitable, right? Because you can discriminate something that's much more precise than the representation of individual neurons. So population coding, what's a consideration? So let's think about the simplest case. Here you have some variable, firing rate of a neuron as a function of some variable. It could be movement direction of the hand or orientation of a bar, whatever variable from outside. Let's imagine you look at like 2 cases. In this case, each Gaussian curve plot a tuning curve. Basically, the mean firing rate of a neuron is a function of that variable. Right? It likes some particular value of that variable, just like have a preferred direction in the motor cortex. Of course, you have many neurons. Right? The one consideration is that if I only look at single neuron, in this case, on the top, the tuning curve a little bit wide, and the bottom a little bit more narrow. Right? If I only look at a single neuron, the neuron is slightly shaded. If that cell fires, so which neuron gives you more information about the value of the particular variable? You say the lower case gives you more information in the sense that if that cell fires, you know that your variable must be located somewhere within this range. Right? It's not possible to be very far away. All right? For that individual cell, is more narrow tuning, give you more information. Give you more precise information where that thing is located. Right? But on the other hand, if you use the whole population, the picture may become different. And there's another consideration. So given this variable, this value, say over here, if I ask you what are the cells that are activated at the same time? Well, the cells are activated only if their tuning curves have significant overlap with that location. Right? If the cell, think over here, if my variable is here, this by definition this cell is not going to be active. Right? But in this case, if you're wider tuning, you will activate more cells at the same time. Right? So each cell gives you less information, but you will pull information from many more cells at the same time. It turns out these are 2 conflicting factors. So it can make even for high dimensional space. It turns out it's actually pays to have tuning that's very wide. You activate many cells. Actually give you maybe counterintuitive, but actually can give you more accurate information. In the one-dimensional case, the case is actually, it favors more narrow tuning. Narrow tuning actually is actually better. The two factors depend on how many neighbors you activate. In high dimension, you activate more neighbors. All right, so these are just some general considerations. I'm going to tell you this one example. Focus on one example, cosine tuning, because this historically this is the first decoding algorithm about population vectors. It's extremely simple, but I think it's good to actually understand the simplest thing first, right? In this case, we sort of quantify the firing rate of a neuron. This is the sort of formal expression. That you say that the activity of a neuron, right, is a cosine function of the reaching direction. So this is basically it's a dot product. All right, you have a preferred direction, P is a vector. The R is the reaching direction of the hand. All right. If the two vectors are aligned, the dot product has the highest value. Right? So if you express that angle and amplitude, it becomes this. So the amplitude of the two vector product times the cosine of the angle between the two vectors. Right? This is just dot product. So that's the cosine tuning. It turns out also this also implies that your activity also proportional actually it's proportional to the reaching velocity. But this is like a more advanced topic. But of course, you see this. The dot product can be positive and negative. Your cosine function is from -1 to 1. Right? If you're in the preferred direction, it's positive. You're 90 degrees away from preferred direction, it drops to 0. You go more than 90 degrees, it becomes negative. Right? So the real activity is a positive, right? At least it's non-negative. It can be 0 positive. So you usually add a constant, so like a baseline fire rate. So this activity here means activity above that baseline. Right? It's basically the middle of that cosine function. All right, the population vector is very simple. Suppose I observe a bunch of neurons, the activity. I haven't measured their preferred direction. Then I just do this weighted sum. So this is vector T has a scalar coefficient, which is activity that is known. Then people argue if you just use this, then you can recover this vector, the population vector, and the weighted average of the preferred direction, the weight of actual activity above baseline. So this vector is always a vector. It turns out this vector is probably the same direction as the activity direction. Under some condition I can explain in the second. So this is an example of how this will work in practice. All right, so each black line here is the preferred direction of a single cell. So here there are many cells. There are hundreds of cells that collected in many different structures. Put them all together. So this, if you look at this line, so this is preferred direction of a single cell. So the plot, this plot is arranged according to the reaching direction. The middle of the reaching to the right. The middle of the reaching to the right, which is actually direction in the direction. The red line is the population. So what's important? So each of the black line is, if you look at the coordinates, this is AI times the TI. So this is the preferred direction reaching of activity. So this is our fixed to the right. So this one. This measures the preferred direction. The point always of the this cell is always pointing the same direction. This one is so basically it's always pointing the same direction, but the amplitude of the vector is proportional to that activity, right? Above baseline. All right. So this cell the vector for the same cell. This is preferred direction of the same cell divided by activity. Each different case is moving in different directions. When you add them all together, this red arrow is the company. When you add them all together. So like this, if you move this is actually moving direction. So all the cells in that direction will have more activity. Right? Then because this is like a volt, you add up all the volts. So the cell in like this direction require more. You add them together to expect the whole. There are errors, not exactly right, but it's just to make the operating work. So this is the simplest demonstration of population vector. So this also works in 3 dimensions. So this is the example that if you space, you find a shell in multiple pictures. You have particular direction in all directions. So it's pretty unique. And if you're, vector form, you average all the preferred direction, weight. It's very similar to the activating direction in the 3-dimensional case as well. Right? So how does this thing work? The mathematics is actually very simple. So this is the condition. It depends on the preferred direction. If the preferred direction is if you do this is the output product I talked about before. It's a matrix. If this matrix is identical matrix, well, how this is specified. This will be the case. You could be uniform in all kinds of directions. Average it's approximately identical matrix. It could be other case, like even they are like as long as you have the second order correlation vanishes, you get this. The vector form, and I put the A on the right side because scalar doesn't matter, but this makes things much more convenient. You put this way, and then you get rid of R is the same in the sum, you get it out, so you have this form in the summation. If the summation is the identity matrix, then your population vector is equal to your reaching direction exactly. That's a very simple argument. You may ask us, why this is useful? Because you already know where the animal is actually moving, right? Why do you want to, go all the way to record all the neural activity and then just, okay, I can recover that direction? Well, of course, it's not very useful in this way, but it can be useful in other examples. This is the early example. This is called mental rotation. So mental rotation refers to, a three-dimensional figure like this and another one like this. People ask you, are these two identical? You can do routine in your mind to see whether they're identical or not, right? You give the answer. It turns out the reaction time is how much time you need to make a decision that depends on angle in the two figures. Have a very interesting linear relationship. As if you're in your mind, you have some speed, you're rotating them. You're very closely charged, you can rotate very quickly and make a decision. This is called like a mental rotation, right? In the motor system, there's a simplified path for the monkey. So in this case, what it shows that the monkey's pen, this path, monkey's pen in the middle, right? You show the animal a visual stimulus somewhere along a ring, in all possible direction. Once you show, usually, if you show, light, the monkey's hand is supposed to move it, all right? In this case, the task is slightly different. The monkey will learn to, instead of moving towards the visual stimulus, you move it 90 degrees to the left. And that's a rotation. So if you do this, you can see with the population vector, because population vector, give me one time measure the preferred, looking at a neuron or all the neurons, right? Then, just based on activity, I can reconstruct the population vector. So what happens is this. So in the beginning, so all the cases, this is like a 20 milliseconds, very fast, right before movement, right? It's a very, very fast time. There was no movement. Okay, that's important. If you're not the animal that's prepared to do movement, but the hand is not moving. The muscle, there's no EMG, there's no movement whatsoever. Right? It's just very happening inside the muscle. So what happens in the beginning? you can already see there is some activity already. You do the vector, you see a vector that's pointing in this direction. It's small, but not very long. Eventually, it grows. At the same time, you see it rotates towards this direction. The final direction is actually, this all happened before animal even had a chance to make a movement. Just having a head very fast. Then, initially, it is then at a bigger sooner, and then it rotates in the back. So this shows that quantum vector can use to read out the information and interpret in a way even before the actual movement. Right? Otherwise, it's just like, why do you want to do that? So another thing can be used to do use a population vector try to drive a robotic arm. Right? Because once the motor system has a command and move this way, you can drive something else. So this is from Andy Schwartz, who's a guy who did a lot of work in this area, and also now is actually in brain machine interface. So in this case, he's recording from this is a single neuron in the motor cortex. While the animals move the hand in a circle, first you see the Poisson nature spike, very random, right? It's just like an oscilloscope recording. There's a spike triggered. It's in the motor cortex firing while the animal is doing the hand movement. There's not much to show. So in this case, what he used is that, I don't remember which is which. So basically, you can use population vector moment to moment, just like in that mental rotation task. Each short time window, I collect activity in many neurons, I construct where is the population vector. And use that, you can, the population vector give you linear movement, so the small velocity, small displacement. You add them, head to tail, then you can construct the trajectory of movement of the hand, right? In this case, the animal is moving, this is the same thing. You see the spikes. So this is a virtual reality movement. The animal is moving a cursor to move, and that you say that in a three-dimensional virtual reality space, the movement of the population vector is very similar to the actual kind of movement in this case. So this is a similar thing. This is an early example. So on the right-hand side, you see the animal is pushing the button and move around. And you record from many neurons at the same time. So the robotic arm is actually, in this case, driven by the population vector. The movement, you can see at least some correlation. The animal, the actual hand movement, then you see you record activity from the cortex. Based on what we know, if you're able to drive it, put it back to the point in the same direction the actual kind of movement. So you use that signal, the thing works perfectly. The arm can move exactly the same as the real arm, right? So in that case, it's already been not very good. So we have another example like this. This one is better. So in this case, this is a robotic arm. So the animal's arm is actually not moving. This is not amputee. The animal is learned to think about movement. That hand is actually not moving. So it's pretty good. It's a gravity and moves the hand, putting the mouth. It's not perfect that it's very mobile. It's not totally working. Let's do something useful. Change a different direction, a different location. I think so this is the base layer research. It's sort of working, but except for in this case, the little finger can snap. So it's not perfect, but you see that. So based on the population, then you see how documented you measure the spatial direction. So you may ask, what is this population vector really the best method? Because you see there are errors in the example. It's not perfect. What would be the best method? The best method is called the maximum likelihood. So this one possible generation is doing it this way, so that So okay, so this is the sort of population vector, which is paraphrasing. Right? The population vector is basically that dot product. Dot product is basically cosine function. So effectively, you are doing this bunch of cosine function. They're angled, peak at the preferred direction. This is a two-dimensional case weighted by activity. So that population vector is important in finding the peak of this sum of this function. In general, you don't have to use the cosine function. How about use other kind of functions? Other function, you add them and you find the peak. You can do this kind of trick. And also do this for the linear estimator. We talked about this. Use optimal linear mapping. You can use that trick too. So use this pseudo inverse trick. So I'm not going to talk about the details. It's very similar. So if you use that, it's still linear. There are other methods more accurate. So one thing I want to say that there are many ways you can do this kind of thing, but what is the best one? The best one, whenever you encounter this kind of problem like parameter estimation, the first thing to think about is a maximum likelihood. It has many good properties. So it's almost optimal in the sense that you always find a probabilistic model for your data. If your data have noise, right, in there with Gaussian noise or Poisson noise, whatever noise, and you have some parameters, right? And then you want to estimate that parameter. Of course, the standard method is the least square. Right? Least square that you assume you have a bunch of you have an input-output model, the linear function, right? You have a Gaussian noise. So then, given this parameter, that's your slope and your intersect AB, your distribution of your output have this Gaussian distribution. If they're independent, the probability multiply like this. It's equivalent to you have exponential function. There is this quadratic term in there. So to maximize, the maximum likelihood idea is that to maximize what? To maximize the likelihood, to maximize the probability of the data, to make the data most likely. So that's the parameter you should pick. That's the idea. So in this linear model case, what does A and B actually pick? Make my data most likely. So your Y is data, your X is input, output data, you already have that. Just make this probability the highest. So basically, this quadratic term, because the negatives are, make the smallest. So this is the same as you minimize this. Also, Gauss is also the person who proposed the Gaussian, and also he's the one who first pointed out the relationship between the least square method and the Gaussian. This idea. But what is about this idea, like like a population vector like this, or more generally like this basis function, to maximize this? How does that relate to maximum likelihood? Maybe they're also related. Let me just show you a little bit. So, suppose in general, you give me some parameter. The parameter here, what's your direction? You give me the direction, and then my activity has some distribution. I assume it has a Gaussian distribution. You give me the parameter. This is my tuning function. This is phi. And this activity. I assume that the difference between them, that's the error, has a Gaussian distribution. If they are independent, then you can multiply probability. All right. Just same as the least square method. If I maximize the probability to minimize the square error term, right? If you write out, expand this quadratic term, you get this cross term and also the square term. Right? So if these activities, the total activity squared and all this tuning curve squared are added together, if they are sort of hold at a constant, then the most important thing is the cross term. Right? So that means if you maximize this cross term like this, then it's the same as you minimize the square error, or the same you maximize the likelihood function. So that's the very simple argument for the relationship, right? Sometimes you use this also work. Sometimes it is equivalent to maximum likelihood method. All right. So another concept is important. I just will mention very briefly. So before I go on, yeah. So I think I gave you a little bit more, but I think you guys are the best student in the university. I give you a little bit more, but it's a nice game. So but the basic method is kind of for machine learning or for understand the perception and understand revenue. It's almost like benchmark method. I call them all the basic method. So these things that the base rule I really call is actually very simple. If you have a neural response R and it's a stimulus, right? So the base rule is that I want to some physical variable. So the rule looks very simple. That you, based on the probability, joint probability of response and stimulus, right? You can split up into either way, either this way or that way. It's a conditional probability. So basically, just given each stimulus X, how the things actually distributed, your response distributed. Times how that stimulus distributed. So this is just like this is the standard conditional probability. There are two ways to write that. So based on this, you can write the equation in this way. So this doesn't seem to be very useful, but that turned out very useful in the sense that it's look at this. So here, the given stimulus, how the response is distributed. So this would be you can measure in experiment. You try different stimulus, different physical variable. You can control and see how the neuron respond. You can have a Poisson model or a Gaussian model with any other equivalent model. So this part can be measured. The distribution of the stimulus can determine the average. But in the real world, the distribution is actually very interesting. I don't have time to talk about that. Is that people usually assume that can be used. But this can also be measured. This in the outside world also so this is the probability of the response. This can be derived from sum over our response. I'll show you that. But basically, this is really just two things you can measure. This is response. this is very similar to this messing mechanism. All the these are the data that reflect the mechanism. If your stimulus weird. Color. Why is this useful? The same as cognitive action. So I'll show you this example. So this is from David process. This case we got from your recent Nature paper. So in this case, the animal is running a two-dimensional environment. So when this spot has food wells and gave a food to the animal is running. You see this color stuff is the posterior distribution for the solution. In this case, the animal is not moving. Okay, this is very fast. You can see 20 times slower. In this case, the animal is stationary. So you don't have to repeat it. moving curve is a fraction of a second during that period. So the activity is
but you want to show that some animal movement sometimes go there, sometimes don't go there. But in many cases, they look at the last line where you follow that. But you need to be more systematic to do stuff. For example, if I say find food by opening up a new path, you think about it first, and then you follow that with the water. That's all right. So that's all.